Hi everybody, welcome back to another My Tutor Online Schools tutorial, GCSE Maths, and today we're going to be going over a graph summary. So for the past 2 weeks we've been going over a lot of stuff to do with graphs, so today we're going to kind of bring it all together, summarize it, and just do a lot of exam style questions and briefly go over everything. So this session will last 1 hour, so it will go on until 3 p.m. and the last 15 minutes I'll take a Q&A, so you can give me any kind of graphs topic that we've been over and I'll answer any questions that you have. So this is me, I'm Molly, I'll be leading this session. I'm currently studying computer science and maths at Bath, and I've done a lot of lessons with my tutor, so quite experienced in this stuff. So throughout the lesson, please do whack any questions that you might have either on the Q&A or on the chat at the top. And I'll pick them up as we go along. If there are any longer questions, I'll come back to them at the end, like maybe a specific past paper question that you want me to go over or something, but I'll pick all of those up at the end. Cool. So I think it is 2. So I'll get started. So this is a list of everything that we have covered in the past couple of weeks, which is a lot of stuff. So how to use y equals mx plus c. So that's the m is the gradient and c is the y-intercept. So we've been looking at how to interpret straight line graphs using that. And also thinking about parallel and perpendicular lines. So when lines have the same gradient, they're parallel. And when the gradients multiply to give -1, they're perpendicular. So they meet at an exact right angle. Then, oh my gosh, I've used the wrong type of 2. Finding the gradient between 2 points. So this is when we have our either 2 points on a graph and we draw our triangle, or when we have 2 points and we use difference in y divided by difference in x to find that. And then this is the main one that I want to cover today, actually, because it's the most common type of graph question, which is how to find the equation of a line. So this is, if you were at that session, you'll remember the kind of magic formula that I kept banging on about, where you can find the equation of a line from just the gradient and any point on that line. So it's a really useful formula. So we'll go over some quite tricky questions to do with interpreting the questions themselves and using what we have to find the equation of a line. Then we looked at solving simultaneous equations using graphs, so where you plot both of them on, and if it's a quadratic, you kind of sketch it on as much as you can, and then we can either solve if they're straight lines or estimate if one of them's a quadratic, the equations, the solutions to these simultaneous equations based on where the lines meet. Then we did distance time graphs. Gosh, we've done a lot, haven't we? Then we did distance time graphs. So this is where we kind of start to apply it to the real world. And we think about how the gradient means the speed. So if you've got a steeper gradient, it means they're going quicker, and so on. And we even looked a little bit about speed time graphs, where the gradient there is the acceleration. So a flat line means a constant speed, and so on. So these are useful for, as I said, looking at real world situations. Then we did 2 lessons on transformations, so especially looking at the function notation of transformations. So this is when we have y equals f of x, and then a shift is represented by y equals f of x plus a, and so on and so forth. And then finally, yesterday, we looked first of all at cumulative frequency diagrams. So that's when the lines are constantly increasing. So at each point, you plot the frequency up to that point. So it grows and grows and grows. And from that, we actually looked at some box plots as well. So when we had to find the median and the interquartile range and find that. And finally, histograms. So this was where you plot the measure against the frequency density, and then the area is the frequency. So it looks more like a bar chart type structure, where you've got bars of different widths and different heights going along. And we use that to interpret data as well. So for 2 weeks, that's a heck of a lot of content. So well done if you've come to them all. If there are any on here that you've missed, do check out. They're all on the My Tutor YouTube channel. So do check those out, because yeah, I'm only going to be going over in brief detail today, and the ones that I think come up the most, and the ones that I think are the best to get a good grasp of. So yeah, stop me if you think I'm going too fast. That's one that I've been getting less frequently, but it still happens. And like I said, pop on any questions as we go along. So we're going to start by covering some, like I said, so this section here, finding the equation of a line and using kind of those y equals mx plus c type trick, so calculating the gradient, parallel, perpendicular, and so on and so forth. For example, quite a common exam question would be, so I'm going to do one exam question, then I'm actually going to find some graph exam papers online. I didn't have time to get them up beforehand, but I know where to find some, so that's fine. So let's say we're going to have 3 points. So A, B, and C. What is the equation of the line which passes through the midpoint of AC and is perpendicular to AB? So this one's, I think, reads quite confusingly, but we're also going to try to do it without sketching it, just to prove to you that you don't need to sketch it to answer these questions. We can actually do it just from what we know about the points. So the first thing to note is that we're looking to find the equation of a line. So that means we're going to need our magic formula, which I'll write it down when we have to use it, but what it involves is needing the gradient of our line and a point that it passes through. So let's first of all think about the gradient. Well, it's perpendicular to the line AB. So we can tell what the gradient is if we know the gradient of AB. So let's do that. So we've got our points A and B here, 3, 2, and -1, 9. And if you remember finding the gradient just from looking at the points without actually having them plotted, is the difference in y. So we're going to take the y value from A minus the y value in B, that's just what the difference is, divided by the difference in x. So the x value in A minus the x value in B. So we get -7 divided by 4. So this is what the gradient of AB is. So I'll write this in a different color so that we can see what's the gradient of our line. Well, if you remember, when they're perpendicular, they multiply to equal -1. And what this means is it's the same thing as flipping it and making it negative, or rather multiplying it by -1. So here it already is negative, so we know that our gradient is going to be positive. So we just flip it and get rid of that negative sign. So the gradient of our line is 4/7. So hopefully that makes sense. Yeah, someone got the correct gradient for AB. Well done. Yeah, always if you want to pop your solutions in the chat as we go along, it means that you can kind of check that you've got it before maybe I say it. And also if you put in something that I can tell is a common mistake, I can explain where you might have slipped up there. So this is brilliant. We've got half of what we need. We've got the gradient of our line. So now we just need to know a point that it passes through. And it tells us here that it passes through the midpoint of AC. Now, the midpoint is found by finding the midpoint of x and the midpoint of y. And we find the midpoint of two numbers by adding them up and dividing by 2. So for example, if you wanted to find the midpoint of 8 and 10, we can tell just by thinking about it that it's going to be 9. But to prove that, we add them up, 18, and divide by 2. It gets us 9. So that's what we're going to do. So the x value of our midpoint is going to be 3 plus -4 divided by 2. So there, I've taken the x value of A and the x value of C, because we're looking for the midpoint of AC, and divide that by 2. And that's equal to -1/2, because it's 3 minus 4 is 1. -1, sorry. And the y value of our midpoint is going to be 2 plus -4 divided by 2. So again, I've taken the y value of A and the y value of C, added them together and divided it by 2. So that's going to give me -1. Which means that the point that it passes through, which I'm going to call, I'll write it in blue just so that it's consistent here. We call this x1, y1, because that fits with the notation of our formula. And that's going to be -1/2 -1. So that's the midpoint of AC, and that's what it passes through. Okay, cool. So now we've got the information that we need, and we're going to use this equation. So I'll write it in green here. So it's y minus y1 equals m lots of x minus x1. And write this one down. If you're going to take anything away from this lesson, I probably said it when I covered it last week, this equation. Because this, like I said, if we just have a gradient m and a point that it passes through, x1, y1, we've got the equation of the line. And that's pretty cool. I think that it gives us a really, really nice way to just immediately see what we're dealing with, what line it is that we're dealing with. So let's just go ahead and substitute in the information that we have in here. So we get y minus, well, what's our y1 value? It's the y value of the point that it passes through, so it's -1 equals, and then what's m? It's here, it's the gradient of our line, so it's 4/7. And then x minus, what's the x value of the point? It's -1/2. So this is what we get. Now this is a perfectly valid equation for a line, but it doesn't look the nicest. Normally these questions, and I forgot to put it on, would say give it in the form y equals mx plus c, for example, or maybe something else, but normally they'll ask you to give it in that form. And that's what we're going to do, because then we can tell a lot about the line. We can picture what the line looks like if we know it in the form y equals mx plus c. So let's just go ahead and kind of simplify this a bit. So first of all, wherever we have a minus, we know that that just becomes a plus. So this becomes, I don't know why I wrote 3, y plus 1 equals 4/7 of x plus 1/2. So already it looks nicer. There's a lot fewer brackets, and it seems a lot better. Then what I would definitely recommend doing at this point is we're going to multiply up by 7. And that seems kind of counterintuitive because we just want it to be y equals mx plus c. So why would you make it be a 7y? I went into this in more detail last week when we were doing this kind of stuff for the main lesson. But the reason is because otherwise we have to deal with fractions, multiplying 1/2 by 4/7 and then subtracting the 1. So it makes more sense to make everything non-fractional and then divide if we need to at the end. So we're going to multiply everything by 7, and that gives us 7y plus 7 equals 4 lots of x plus 1/2. So that's all I've done. I've multiplied it by that 7. And then I'll expand out the brackets on the right-hand side. 7y plus 7 equals 4x plus 2. 4 times 1/2, it's just 2. And then we're really nearly there. But we only want y on this side. We don't want this plus 7. So we'll subtract 7 from both sides. And again, at every stage of this has been a totally valid equation because they all mean the same thing. We're just making it a bit nicer for us. And then finally, I'm going to divide everything through by that 7. So y equals 4/7 of x minus 5/7. And that is the equation of this line, which has actually worked out quite nicely considering our question was this horrible kind of passes through the midpoint, is perpendicular to this. And we can see the gradient is 4/7, just as we said it would be. And this just means that the y-intercept is minus 5/7. So it's got a positive gradient and it intercepts the y on the negative axis. So hopefully that makes sense. Someone said, how do you become good at maths? Practice. And if you practice it enough, I think it becomes a cycle. If you practice it enough, you get good at it. So you actually start to enjoy it. Once you get good and you start to understand the questions, I promise it does become very enjoyable. And then you want to practice it more and so on and so forth. But you might also just be here because your teacher's forcing you. That's fine as well. Let's have a go. I'm just going to get up some generic exam past paper questions. That's all I'm going to search for. GCSE Maths graph exam questions. And also this shows you my process of how I find the right ones. So I might have a look on here and see. I just kind of want a combination of all of them. I don't want Let's have a look here. If not, I'll just get them from different ones each time. No, that's bite size. We don't want that. Please do let me know if there's a specific topic that you want. So everything that I have is here. So straight line graphs, real life graphs, quadratics, and so on. So what I'll go to is this one. But do shout in the chat. I'm happy because it's a summary, I'll let it, totally be led by you. Okay, do I want to do this one? So this is interesting because part of it is kind of like some of the content that's actually going to be covered next week. But that's why it's like a teaser trailer. Wow. So this is like when we were doing solving simultaneous equations using a graph. So this actually lays it out for us. It says sketch these things on the graph and then use that graph to estimate the solutions to the pair of simultaneous equations. And the reason that it says to estimate those is because we've got a quadratic in there. You see we've got an x squared plus y squared. So we know that that's not going to be a straight line. And that means that we're not going to be able to precisely see anything. No one can draw these things perfectly. So I'm going to actually start by sketching the line B. So y equals 3x plus 4. And the way that I'm going to do that is just by plotting a few points that would be on there. So if we have a look here, I'll plot this one in pink, why not? We just think, well, when x is something, what's y? So when x is 1, well, y is 3x plus 4, so that's 7. When x is 0, y is 4. When x is, let's do minus 4. We'll do those three and plot them on and we should be able to see what we're doing. When x is minus 4, y is minus 4 times 3, that's minus 12, plus 4, that's minus 8. So let's go ahead and plot these on here. So the first one is the point 1, 7. So I'm just going to zoom in to make sure that I can plot it, okay? 1, 7 is here. Next point is 0, 4. Well, we knew that it would be here anyway because it's a y equals mx plus c. So the y-intercept here is 4. And then finally, minus 4, 8. Minus 4, minus 8. Now, what you can see from this is that we only actually needed 2 of those points to be able to plot a line. If you take 2 points, there's only one line that goes through both of them. But we could have made a mistake with one of them, so we want to really make sure that we have at least 3 points. Because otherwise, yeah, we could definitely have made a mistake. So then I'll just, oh gosh, that was very bad. Join these up. Making sure that it goes kind of like through them both, through all of the points, but extending out. There we go. Brilliant. So this is that line B, y equals 3x plus 4. And hopefully you can see how I drew that. Now the line x squared plus y squared equals 25. We're actually going to be covering this next week. So I'm just going to tell you for now because it doesn't really affect the rest of the question. But this is a circle. And this is a circle, center 0 with radius 5. So if you don't understand that now, don't worry. Just maybe pretend that that was already kind of on there. This is going to be difficult to do. Okay, that wasn't too bad. Cool. So this is what that one looks like. As I said, if you don't understand why that is, please do come next week to one of the sessions that will be on your timetable. Or just believe me. So I mean, if you want to, you can look at these 4 points here, 5 on all of the axes. Well, when one is 0 and the other's 5, 5 squared is 25. So you can believe me that these 4 points are true, and then see that that kind of connects to make a circle. So now what we can do is think about estimating the solutions to this pair of simultaneous equations. So what this means is that the both of these equations are true. So let's first of all think about this straight line where y equals 3x plus 4. Along every single point on this line, y is equal to 3x plus 4. That's what the line means. It means that this equation is true at every point along this line. So the solution is somewhere along this line. or rather solutions, because it's we've got a quadratic, we know that there's going to be 2 solutions. And furthermore, x squared plus y squared equals 25 is true all around this line, all around this circle. Again, by the very definition of why we drew it. So the solutions are on this line and on this circle, which means it must be where they intersect. So we can see the 2 places where that is. The first one is down here. So we kind of see where that is, draw down to it, and across and see where this is. So I would say that looks like minus 2.8-ish there and minus 4.2. That looks kind of reasonable. And then find the other point here. Again, see where it lies on each axis. So that looks like 0.5 here, and maybe it is roughly 5 there. So that's kind of what that looks like to me. So those are our solutions to our equations. So the first one down here being x equals minus 2.8 and y equals minus 4.2. And the second one being x equals 0.5, y equals 5. So hopefully this makes sense as to why. And in fact, we could solve these precisely. Equations solver. I'm hoping that I can find one online. Because then I can kind of prove to you that these are actually quite accurate. So yeah, equation 1 was that x squared plus y squared equals 25. Oops. And the second one was y equals 3x plus 4. I don't know if it will like the squares in that. Oh, this one doesn't work. Okay. I'll try one more, and if not, we'll just move on to another question. I just thought it would be interesting for you to see. Oh, okay. Yeah, okay. X squared, X squared. Oh gosh, maybe this is going to take too long and freeze my computer. Yeah, there we go. X squared plus y squared equals 25, and y equals 3x plus 4. I feel like a teacher trying to use technology. That's awful, isn't it? And it will give us, so what are we looking for? Minus 2.8 and minus, oh, that's supposed to say 4.2. And 0.5 and 5, or something roughly equal to that. So, do you want to give us these in decimals? Everything's gone wrong today, hasn't it? Okay, but we'll assume that those are what those are in decimals. Have a look yourself. Maybe we'll calculate it and work it out. But they will be like that, I promise. So, okay. Someone said, can we do quadratic graphs, please? Sure thing. What kind of things with quadratic graphs? So sketching them, or what they look like? While you answer that, someone else has asked. Okay, sketching, cool. Someone's asked if I can, show these on decimals. Actually, that might tell me the point as well. So if this is kind of the best thing that I can show for graphs as a good summary. I think I've used this almost every single session. It's just a graphing calculator online. So it's really fantastic at showing you what graphs look like. So if you ever get confused or aren't sure, this is a really good thing to do. So here, and in fact, yes, see, I should have done this in the first place. 0.33, 4.989. There you go, that's pretty close to 0.5 and 5. And the other point here, minus 2.73, minus 4.189. That's super close to minus 2.8 and minus 4.2. So I think we smashed that there. So yeah, I should have done this in the first place, decimals. And you can see that this is exactly how we sketched it there. Cool, hopefully that makes sense. And thank you to whoever recommended that one. Definitely better than trying to use that other software. Cool, so someone's asked about sketching quadratics. So we can definitely do one like that. Let me just grab up one that has with a graph. Yeah, cool, perfect. Okay. Let's go over this question. Again, I'm trying to get ones that you definitely could get in an exam. So these are kind of non-exam board specific, just generic questions that you could get in anything, and they're worded like exam questions would be. So part A here, it says to plot the graph of y equals 2x squared minus x. So what we're going to do is really similar to how we did the line, but with a lot more points and kind of a lot more consistently spaced, is that we're just going to work out some points that would be on there. So let's see what x values we have along here. We could go right from minus 10 to 10. I think what we'll do is just maybe do minus 10, minus 7, minus 3, 0, 3, 7, 10. I've just kind of done some fairly like regular spacing-ish, and it should give us a good idea. And then we'll see what y is at each of these values. And hopefully, yeah, and if you're still not sure when you've done these, like pick some random ones, then pick some more. Maybe start doing minus 8 and minus 9 and so on. So our equation is this: y equals 2x squared minus x. So we'll take our first value for x, which is minus 10. So x squared, that's 100. Oh, we're not going to be able to plot this, are we? X squared, that's 100. 2 lots of that is 200, and minus x is 210. So that's definitely not going to go on there. So actually, immediately telling from that, maybe I should have chosen some much smaller ones here. Perhaps I'll rechange what I do on here. So you see, it's a lot of trial and error working out which points to choose. So let's go from minus 4 and do every one back up to 4. Okay, so when it's minus 4 squared, that's 16, times 2 is 32, minus 4 is 36. So that one, we know that it's 36, so we know it's really high, but we can't plot it. Minus 3 squared, that's 9, times 2 is 18, minus 3 is 21. So again, too high for us to plot on here. Minus 2 squared, that's 4, times 2 is 8, and then minus 2, that's 10. So this one we can plot. Minus 2, 10. Minus 1 squared is 1, times 2 is 2, minus 1 is 3. So do let me know, whoever it was who asked to do this, let me know if I'm not explaining it right. So then when x is 0, oops. When x is 0, we have 0 squared, which is 0, times 2 is still 0, minus 0, still 0. 1 squared is 1, times 2 is 2, minus 1 is 1. 2 squared is 4, times 2 is 8, minus 2 is 6. 3 squared is 9, times 2 is 18, minus 3 is 15. And again, these go above, so we won't be able to do that. Brilliant, so people are getting those in there, which is fantastic. So let's plot these in. So we can't plot these, but we can start plotting from here. So let's do this in a different color. So minus 2, 10. So let's find minus 2 here, go up to 10, and pop that one on. What's the next one? The next one is minus 1, 3. So minus 1, 3. What's the next one? 0, 0. That's a nice one. 1, 1. 2, 6, and 3, 15. So 2, 6, and well, 3, 15 is too high. So this seems like a really weird scale for them to have chosen because it doesn't fill it very much. But then what we do, we can kind of see how this is going to look. And it will kind of look a bit like that. So hopefully that makes sense. You can do more if you wanted to as well. You could even do like 1.5 and 0.5 and stuff like that. This is definitely not the easiest graph question, and I'll do another one after this because it was a couple of people who requested this. So I'll show you what it looks like on Desmos. Should just keep this tab open really, shouldn't I? So y equals 2x squared minus x. So there we go. Yeah, it looks like this. In fact, this is interesting. Yeah, this shows that it goes actually slightly below. So maybe I should have thought about different points here. It does actually go slightly below that x-axis. So I actually sketched it slightly wrong and it should have gone a bit below. I think, I mean, you're only expected to do whole numbers, so you would still have been fine with that. But hopefully you can see that that makes sense. And then it says, use your plot to estimate the solutions to 2x squared minus x equals 5. So this is no different than kind of solving equations, solving simultaneous equations on a graph. So here, we want to think about what we're comparing it to. So what this basically means is that we've got this line y equals 2x squared minus x. If we then also have the line y equals 5, then when those are equal, because the y's are equal, I'll show you what I mean. I'll write them down. It's a very hard thing to express. So y equals 2x squared minus x. And then if we plot the line y equals 5, then that kind of, because these y's are equal, that means that 2x squared minus 5 equals 5, where they meet. So if we draw the line y equals 5, which we know is here, because at every single point along this line, y is equal to 5. No matter how far you've gone across, the y value is always equal to 5. So the points where they cross, oops, oh gosh, I didn't know you could do that, right. The points where they cross are here. So let's see the solutions. And remember, it's only looking for solutions to x, because we know that y is equal to 5. So the solutions are kind of here and here. So what's that? Minus 1.6 and 1.9. So now let's see what they actually are. They are minus 1.351. So that's a bit far off. And minus and 1.851. That's fairly close. And I think you'd still get marks for that. I might get some deducted because I didn't do it going just below here, but yeah, I think that's hopefully makes sense. Hopefully. Cool. So I was just thinking the other way that you could actually do this to plot it exactly, rather than just estimating points, is we could think about where it's going to cross the x-axis. So we've got this line y equals 2x squared minus x. It crosses the x-axis where y is 0, right? Where it hasn't gone up at all. So then we just need to think about what's 2x squared minus x equals 0. Well, we can factorize an x out of that. And then if you remember about solving quadratics, then either x equals 0 or this one's equal to 0, so x equals a half. So actually we can tell that it's got to cross the x-axis at 0 and a half. So there we can tell it has to go below a little bit. I did that quite quickly, so I am going to do another one, but the couple of people who asked me about sketching those, is it making a bit more sense? Oh yeah, cool, someone said they understood it, brilliant. Cool. Let's see. Let's have a look at graphs and tangents. Let's have a look at some level 8 and 9 questions, because I think you guys can get this. Oh no, right, no, we're not those, because we're covering that next week, so maybe not. Oh, here's a whole sheet called Sketching Quadratics, so let's have a go at one of these. And while I'm going through this, could somebody just let me know if there's a topic that you want to cover next? Oh, okay, right. I'll do this one. I'll do this one. Cool. So after I've done this one, someone's requested real life graphs, so distance and time. So I'll go over some of those next. So this one is just introducing something I can't remember if we've covered before. I think we have. So have we covered completing the square? I think it was one of the first weeks. So basically that's going to help us to find the turning point. So I'll go over it fairly quickly, and if you don't understand, hop back to that video. But this is again about sketching a graph, labeling the turning point, the x-intercepts, and the y-intercept. So, well, let's think about all of those, because hopefully if we get those, we'll have a really good idea of what this graph looks like. So the y-intercept is going to be when x equals 0. So when x equals 0, y just equals 8. Hopefully you can see that from there. So the x-intercept is where x equals 0, and when x is 0, these terms get wiped out, so y is equal to 8. Someone's also requested frequency polygons. So yes, that's a really good one as well. So I'll do some real life graphs and then frequency polygons. So that's where this y-intercept is. The x-intercepts are going to be where y equals 0. So where x squared minus 6x plus 8 equals 0. So the first thing that we're going to do is factorize this. So I'm going to just do the factorization, but go back to just because that's not what this session is about. The reason that it is because these two add up to make 6, minus 2 and minus 4, and they multiply to make 8. But I did do a video on that. I think maybe the first one that I did. So check out that. And then again, because these two things multiply to make 0, one of them has to equal 0. So it's either the x equals 2 or x equals 4. So therefore the x-intercepts are 2, 0 and 4, 0. Now we find the minimum point by completing the square. So maybe I won't do this one yet, just because it's not exactly what we're covering today, but I'll put these ones on for you. So if we just do the scale of one little line is 1, then 0, 8 is 1, 2, 3, 4, 5, 6, 7, 8 here. 1, 2, 3, 4, 5. Here, that's 0, 8, and then it crosses the x-axis at 2 and 4. So we can tell that because it's a smiley face quadratic, it's kind of got to come down here, cross both of these, and go back up again. And if you want to know about labeling the minimum point, I can come back to it at the end if you'd like me to. So just let me know. Cool. So let's go on to some real life graphs. In fact, we can see what the minimum point is here, just in case you want to do it and check. Whatever that was, y equals x squared minus 6x plus 8. There we go. Minimum point is 3 minus 1. If you want to have a go at that yourself and check your solution, that's what it is. And we can see that our points here are correct: 2, 0, 4, 0 and 0, 8. Cool. So real life graphs, where were they? Here we go. These are mostly scatter graphs. Here we go. Okay. Let's go through this one. This is quite a hard one to start with, to be honest. Maybe I'll do a distance time first, but I definitely want to come back to that one. So here we go. I'm going to do distance time first and then come back to that one because that is a really good one to do, actually. Let's have a look at this then. So here's part of a travel graph for Sian's journey to her shops and back. So the first part of this question is to work out her speed for the first 30 minutes of the journey. Sorry, just having a look at some questions. So someone said, for real life graphs, will they ask us to find the equation of a line? No, I don't think so. Oh, someone said we've done this question before. Thank you. I knew that we'd done a similar one. I didn't know that it was this one. No, they won't ask you to find the equation because we don't really use them for that. We'll just go through this question anyway because it's a good one to get us back into it. But so when you're looking at a real life graph, the first thing to ask yourself is, so what does everything mean? So we've got the time steadily increasing here, and we can tell the distance from her home at each point in time. So when she starts, she's at home, so she's 0 kilometers from her house. And then 10 minutes into her journey, she's just over 6 kilometers from her house, and so on. Let's think about what the gradient means. That's always a really, really good thing to think about. And the gradient, because the gradient is change in y divided by change in x, it's always whatever the y is divided by x. So distance divided by time. And we know that that's speed. So a really good thing to note about this graph is that the gradient is speed. So if we want to work out Sian's speed for the first 30 minutes of her journey, that means work out the gradient of the line for the first 30 minutes of her journey. So that's here, going from here up to 30. So we know that well, obviously the length across is 30 minutes. But we want the answer in kilometers per hour. So let's express that as half an hour. And what's the distance in kilometers that she is away? 20. The length of this side of this triangle that we've drawn is 20 kilometers. So the bottom one that I'm doing is this here. And then we just do exactly how we found gradients before. We do 20, so the distance, the y, divided by the x. So 20 divided by a half. And that will give you 40 kilometers per hour. Now, the second part of this question asks us to complete the graph, and she spends 15 minutes at the shops and then travels back to her house at 60 kilometers per hour. So let's put that stuff in. So first of all, she spends 15 minutes at the shops. So she's currently there at minute 45, so she's there until minute 6. Oh, sorry, no. The 15 minutes that she spends at the shops is already on here. So she gets there at 30, she's there for 15 minutes until minute 45. And then she travels back to her house at 60 kilometers per hour. So the best thing to do now is to work out, therefore, what time she'll arrive back. So we know, if we think about our distance, speed, time triangle, like this, we know that her distance that she's got to get back home is 20 kilometers. So any line going backwards means that they're kind of doing negative distance. So if me going to the shops is positive distance, going back home is negative distance. So the shops are clearly 20 kilometers away from her house, and her home is here at 0, so she's got to travel 20 kilometers. And she does that at 60 kilometers per hour. So we know that the distance is 20 kilometers and the speed is 60 kilometers per hour. So that means that the time is distance over speed, which is 20 divided by 60, or 1/3 of an hour. And 1/3 of an hour is 20 minutes. So we know that she gets back in 20 minutes. So if she sets off at this 45-minute mark, 5, 10, 15, 20, she'll get back at 65. So then we just draw that on. And there you go, that's completed the graph. So hopefully that makes sense. Let me know if you want me to go over another distance time one. But I'm going to quickly go over this one here. So this is, as you can see, a 5-mark question. It's quite difficult. Well, it's not too difficult once you get into it. So this graph shows part of Emma's morning walk. Use the graph to estimate the distance she ran during the 30 seconds shown. So, don't know why that came up. Let's think about this graph. Remember, the first thing, look at the axes, see what we're dealing with. So this along the bottom shows time. So it says it's shown 30 seconds, and we can see that there. So at say 18 seconds, she's going about 0.75 meters per second, and so on. And this is velocity. So velocity is a really similar thing to speed, but it's with an associated direction. So what that means is that whereas with a distance time graph, this would mean she was going back. It doesn't mean that with a velocity time graph. All it means is that her speed is slowing slightly, but she's still going forward. If it entered a negative velocity, she'd be like running backwards or running in the opposite direction. But this time, a decreasing line, all that means is that she's slowing down, she's decelerating. So she's running quicker and quicker, she's running quite fast, and then she's still running quickly but quite slowly, then a bit faster, and then she's still running forward, still moving forward at a decreasing pace until she stops after 30 seconds because her velocity is at 0. So it doesn't mean she's gone back to the same point. She's in fact definitely moved forward. because the axes are different. So we had to interpret it in a different way. And yeah, someone pointed out this links really, really strongly to physics. So I think maths and physics go really nicely together. Most people hate them both, but I promise they're both actually very nice once you understand them. And I know that there are fantastic physics lessons as well, so there's probably some good overlap there. So what we want to show is the distance. So again, let's think about our distance, speed, time. I'm going to be kind of using velocity and speed interchangeably. Whoever teaches you physics will want to kill me for that because they are definitely different things. But just in terms of our equation, we're going to use them in the same way. Because this is only positive speed anyway, it doesn't really matter that because it's not going into the negative quadrant. So yeah, fingers crossed Prashayla doesn't kill me. So let's think about our triangle. So it's over speed times time. So we're looking for the distance. So we want to do speed or velocity times time. So to do whatever's on this axis times whatever on this axis is the area, right? If we're timesing two things together, that's the area of something. So here's the kind of takeaway thing from this, is that if you have, and I mentioned it very briefly at the end of when we did real life graphs, if you take velocity time graph, the area underneath the curve is the total distance moved. So let's have a look at what that is. And it just has to estimate, because unless we know the equation of this line and differentiate, we can't do it exactly. So we are just going to estimate. We're going to basically draw some shapes around this line that roughly equals what we're looking for. So there's definitely a variety of different things that you can do. I'm probably going to do some triangles. So I'm going to do one here. Let's do it kind of going there. So you've got to kind of make sure that it goes as, it's only an estimate, so it doesn't matter if it's a bit off. So let's do that there and down. So we'll do that kind of orange bit there. And then I'll do this green bit going here. And then I'm going to do this kind of going, oh no, that's not a nice shape. So we'll do a pink one there. And then finally, so that's like a trapezium there. And then finally, let's do this trapezium here. So that all works quite nicely. It's going to be a little bit of an underestimate because of these bits that we've got here, but you could spend longer making these more accurate. I'm just doing it for speed here. So let's start off. I'm going to do these fairly quickly. Let's start off by looking at this orange one here. So area of a triangle, half base. So that's currently 8. And the important thing is, let's think about what the unit will be. We're doing meters per second times seconds. So it's going to give us an answer in meters. So that's important to think about as well. So half base times, well, the height goes up to 0.8. So this is the area of the orange one. The area of the green one, that's just a rectangle, that's good. So we've got the base here from 16 to 22, that's 6. And it goes up to, again, 0.8. So that gives us 4.8 meters. This blue one here, this is a trapezium, so it's a bit more difficult. But in my first ever lesson, I did that little rhyme for the area of a trapezium. So half the sum of the parallel sides times the distance between them. Follow these rules and you will find the area of a trapezium. So I still sing that to myself in, my university classes if I ever need the area of a trapezium. So half the sum of the parallel sides. So the sum of the parallel sides is going to be 0.8 plus 1-ish, because it's just an estimate. So that's 1.8. Half of that is 0.9 times the distance between them. So here, 10. So that's 9 meters. And then finally, pink, we'll use the same one. So half the sum of the parallel sides. So that's 1 times plus 0.7. Divide that by 2, we get 0.85. And times the distance between them, so times 6. And that's going to give us 0.51. Sorry, 5.1. meters. So these are the areas of all of the shapes, and then we're just going to add all of these together. So that's going to give us 8, 17, 22.1 meters. So it's pretty cool, and that's just an estimate. And as I said, that's probably an underestimate, but I think it's pretty cool that just from this graph, we can estimate the distance that she's run, just from the speeds that she was running over a certain amount of time. So yeah, there's that one. So normally I kind of stop at this point and open it up to questions, but because it's a summary, I've been doing questions throughout. So keep them coming, the areas that you would like me to cover. So I'm going to do frequency polygons next. And someone said, can we do straight line graphs? Straight line graphs as a topic is pretty much this that I was doing at the beginning. So I'll go over it again if people would like me to, or if there's no other suggestions, but I'm conscious of time. I'm not sure, we'll have a look. So we'll start with frequency polygons. So my computer knows what I want to search for. So frequency polygon, let's do it from, I want a question on it. I want one with a blank graph so that I can draw it myself. Here we go. And I want one with different widths. No, I don't think I'm going to get one. Let's just do it on here. So a frequency polygon, just like when we were doing cumulative frequency graphs and histograms yesterday, it's just another way of displaying information. So actually, I'm going to put this on. Sorry, I'm going to put the table and the graph side by side. I think this will make it easier for you guys to see. So yeah, it's just a different way of looking at and interpreting information. So we've got this table of information. So what's this telling us? Let's have a look. Some information about the heights of some plants. So we've got these different kind of ranges, some different classes, we call them. So 20 to 30 centimeters is this class. So there are 8 plants that have the height between 20 and 30 centimeters. And there are 13 that have the height between 30 and 40, and so on. So what we're going to do is kind of plot each of these points. But you can't really plot something in a range as like points. So we're going to look for the midpoint of each of these. So we can add that if we want to as a separate kind of column here to make sure that we're thinking about it. So I'm just going to zoom into the table while we think about this. So the midpoint, if we need to, again, kind of like with the y equals mx plus c, actually, with the midpoint of coordinates, you add them together and divide by 2. Or we can just look at them and kind of see what's in the middle of 20 and 30, it's 25. What's in the middle of 30 and 40, it's 35. And we do the same for all of these. Now, in this case, all of these widths are actually exactly the same. They're all just kind of the next 10 centimeters, the next 10 centimeters, which works for us fine. And then what we're going to plot is the midpoint against a frequency. So the first thing that we're going to plot is 25, 8. So 20, we find 25, we find 8. Then we find 35 and 13. So we find 35 on here and go up to 13. And so on for all of these points. So 25, 45, 45, 25 even. So 45 is there, 25 is here. 55, 10. 55 is 10, and 65, 4. So we've got this kind of, all these points here. And then what we do, which is something that you never normally do, you know, when we were plotting our quadratics, we join them up with a curve. But when we're talking about a frequency polygon, we join them up with straight lines. So that's what we do here. And what this gives us, the reason that it's called a frequency polygon is because it joins, it kind of starts to make, a polygon is just like a shape, a many-sided shape, and we can see it starts to make this sort of shape. And they're super, super useful because we can tell a lot of information about them. For example, looking at a table of data doesn't really tell us anything, but when we look at this, we can see, oh look, loads of plants fall into this middle bracket, and then there aren't as many here at the ends. And you can tell this kind of thing. So one really useful thing that we can do is compare different pieces of information. So I'm sure there's one somewhere, yes, where we can actually compare two different things on the same graph, because we draw two different frequency polygons and have a look. Just like if, just like when we were doing yesterday box plots, we could compare the different box plots and tell different information about them. So let me get the graph and pop this on here. So let me make sure it all fits. Let's plot both of these on here. So the first thing that we have to do is to find the midpoints. So let's do that. So the midpoints here are going to be, let me zoom in on here. We can see what's between 0 and 5, it's 2.5, and 7.5, and 12.5, and so on. So let's pop those on. So 2.5, 7.5, 12.5, 17.5, 22.5. And then we're going to plot, so these are how many minutes late the buses and the trains were. So let's start off by looking at the buses, and we'll do this in, say, pink. So we plot the midpoints against the frequency of the buses. So 0 to 5 minutes late, so 2.5, there were 5. So we plot 2.5, 5. But at 7.5, there were 15. So we go to 7.5 and up to 15. 12.5, there were 4. So we plot that. 17.5, there were 1. And 22.5, 0. And then we can join these up using straight lines. Gosh, it's very hard to get them in the right positions on here. These are some, oh my gosh, these are some atrocious lines, but you'll have to allow me because I'm doing it on a computer. So that's what this looks like. And now let's do exactly the same, but for the train data. So train and the minutes, so it's going to be the same points on the x-axis. So 2.5, and then train is 9. 7.5 is 6. 12.5 is also 6. 17.5 is 2. And 22.5 is 3. Yeah, that was at 3. And then we can join these up with straight lines. Like that. And again, we get these frequency polygons, kind of the starts of some shapes. And then what the question asked us was to use these to compare the lateness of the buses and trains. So whenever we do a comparison question, we have a look at how many marks they are. So this is 2 marks, so we're looking to make about 2 points. So we'll have a look at these. And just by looking at these lines, we can actually tell so much about these. So for example, the buses were late far more frequently. For example, we can see here that the trains, which is this one, there were more trains that were pretty much on time between 0 and 5. Whereas there weren't many buses on time, and there were so many buses late here. So we can say the buses were late more frequently than the trains. However, so that's one of our 2 marks. Second point is that the trains were more frequently much later. When the trains were late, they were a lot later. So for example, no bus was 22.5 minutes late, whereas 3 trains were in this bracket, and more here. So, however, when the trains were late, they were late by a lot more time than the buses. So that's just 2 really simple points. That's 2 marks right there. The buses were late more frequently than the trains, which we can tell from the pink line here. However, when the trains were late, they were late by a lot more time than the buses, as we can see from here. So hopefully that makes sense. It's just another way of displaying data and using it to do that. Someone's asked really quickly, for this question, will we get 2 graphs? No, because it's useful to see them on the same graph. They also asked what happens if something is exactly 20 minutes late. It would go in this one here, which is, you've got to look at the signs. This is less than 20, this is less than or equal to. So that kind of prevents it from being like that. Oh, 25. All this means, because there isn't a 25, because this only goes up to less than 25, it means that of the data recorded, none of the trains were exactly 25. If they were, we would have added either another column or made this. So we've just tailored those to that. And someone's just sent me a joke to finish off on, which I love. What do you call a graph involving sheep data? A bar graph. And we'll end it there.
These jokes are quickly becoming highlights of these sessions.
I love it.
Amazing stuff. Thank you so much, Molly, and thank you all for joining us. Remember, every session is recorded, so you can catch it on YouTube if you need to rewatch. We also do offer one-on-one personalized tutoring, so if you're interested, you can go onto our site to find out more information. Thank you all. Have a lovely, lovely weekend. See you later.
Thank you, everybody.
Bye.